Hello, hello. Oops. Put the chat up. Please be sure and sign into the chat. Oh, geez. Whoops. I'm still getting things set up here, so that's what I'm making noises about. Question I have is, what slide were we on when we left last time? Does anybody remember what slide we were on? What we were talking about? I think, did we do the cost?
We were going to start transformations.
Okay. Get my mouse over there. Come on, mouse. Where are you? Here we go. All right. I'm getting my PowerPoint to that slide right now. So that's probably what we're going to cover today, is all the different transformations we have to deal with. Yep. So oh man, hit the wrong button. That's what I'm complaining about. So let me get a couple of things squared away here on my screen. That one. Nope, wrong one. That one. Okay. So now when I click on the Zoom and do share, are there any questions right now before I get into things? I need to open up my chat window. So if you're talking to me in chat, I don't see it just yet. Okay. I'm still working on getting everybody's, the people who still have temporary access. I'm still working at getting you the everything, the full access code. If you're having troubles with the access code I gave you, please send me an email. Even if you sent it before, I'm tremendously behind on a lot of stuff. If it's administrative, I'm behind on it. So that's my life right now. Okay, cool. I can plug this thing in. I've got so many things plugged into my computer. I'm surprised it doesn't overheat and blow up. Okay. My computer's not reading it right now. And my computer is trying to heat up. The fan is blowing as hard as it can. Poor thing. Okay. So I'm going to get started on this. Use my laser pointer, but you can't see it. Okay. So graphing techniques using transformations. So we're going to talk about what vertical and horizontal shifts are. We're going to talk about what compressions are, horizontal and vertical compressions and stretches. And then we're going to talk about reflections across the X and the Y axes. What's going on there with those. Okay. Before I continue on, we are going to have an exam a week from today, which means what we cover today will be what will be on the exam. So everything from day 1 till today will be on the exam. And that means you will get a review sometime between today and Saturday, and I'll be posting it in files. I will have expected you to have at least attempted every problem on the review, because the day of the review, I won't have time to cover everything on the review. So I only want to answer questions you have about problems on the review. And here's the deal about the review. If it's not on the review, it's not on the exam. Okay. So the review will cover more material than what's on the exam. So I will cover things about, you will have a question or two about transformations, but it may not cover all transformations, where in the review, you will have questions about all the different transformations. Okay. And another thing that's true about my reviews is that the review is generally harder than the exam. So if you can work the review without much difficulty, you shouldn't have a problem with making an A on the exam, or at least a B, because mistakes happen and brain freezes happen. I remember my first grad class, the first exam, I froze over one question, and the one question I froze on, it was just asking, applying, all I had to do was apply the definition of what a group was. And that was the easiest question on the test, and I had a brain freeze on it. And so I didn't answer it. Okay. So I know those things happen. Okay. Any questions? All right. One thing I'm going to add on in here. Let's see if I can see it. I've started doing this in my classes. And so I'm going to go ahead and do it in this one as well. All right. Across the bottom of the screen, it should have, is it there? Is the CC, the closed captioning, showing across the bottom of the screen?
Yeah.
Okay. So I have people in other classes that request that. And so I just go ahead and do it as matter of course now. Probably should go in there and change. I'm wondering if that's a setting in Zoom, I can have it do it every time without having to do it while the Zoom is up. But anyway, okay. So they jump right into showing examples. So vertical shift up is literally just moving the graph up, or vertical shift down is just moving the graph up or down. The X values don't change, the Y values change. So if we look at this, we look at f of x equals the square root of x, and we look at g of x as being the square root of x plus 2. Well, that's the same thing as saying f of x plus 2. So these f of x is the y values, and we're adding 2 to it. So if I add 2 to the y values of f of x, that gives me g of x. So I'm shifting it up 2 units. So if I look at this graph, x, the square root of x, which looks something like this, all right, 0, 0 gets moved up to 0, 2. 1, 1 gets moved up to 1, 3, because the square root of 1 is 1. And so I'm going to add 2 to 1, the y value 1. Where's 4? 1, 2, 3, 4. 4 is supposed to go through 2, 4, and 2, 4 gets shifted up to 4, 4. Okay. And so the graph gets moved up to here. And so it looks like this. It's the same graph, it's just been moved up 2 units. And that's what they talk about here. And so they talk about what I mentioned here, what happened, what it looks like, and what's going to happen to it. So that's what's happening to it. I'm changing the parent function by adding 2 to the y values. This is the change is happening after the square root. So I'm changing the y values. If I did something inside here, then I'm doing something to the x values, and I'm doing before the parent function or before the square root function. But this is being done afterwards. And so boom. And they did the same shifting I did. Only they put the square root of 2 into the calculator and rounded to 1 decimal place. Same thing with the 3. They rounded the square root of 3 to 1 decimal place, and then just added 2 to those numbers. So 1.4 went to 3.4, and 1.7 moved to 3.7. Questions? Yeah. the y-coordinate of a point of the graph of G is 2 units larger than the y-coordinate of the corresponding point of the graph of F. So they're just saying the same thing I was doing, only more formal language. You're adding 2 to each y value. We conclude that the graph is identical, the graph of G is identical to that of F, except that it's been shifted vertically 2 units up, or vertically up 2 units. Okay. The domain didn't change. The domain of F is goes from 0 to infinity. So this is the domain of F, and the range of F is the same thing, 0 to infinity, right? Because the y values, the smallest y value is 0, and it goes up, though the y values are increasing. And so the x values do the same thing. But now with G, my x values didn't change. So that's what they're talking about here. But my y values did. And because my y values changed, it changes my least y values. My smallest y value is now 2. So now my range, my new range, the range of G, starts at 2 and goes to infinity. And that's what the next slide tells us, or the next line on this side. Okay. Sometimes when you have a shift or a compression or something, it changes your domain or it changes your range or both. In this case, all we did was change the range, right? If I have a shift that's horizontal, and that's all that's happening is a horizontal shift, then I might end up changing my domain, but my range usually doesn't change. Now they're going to use the same graph, the same parent function, but now they're going to be talking about, they're changing what G is. Now if G of X is the square root of X minus 2. So that's the same thing as saying F of X minus 2. So now the change again is happening in the y values because it happens after the parent function, and we're changing it by subtracting 2. So each y value of the parent function, this is F of X here, I'm going to be subtracting 2 from each y value. So 0, 0 got shifted down to 0, negative 2, because I subtract 0 minus, and then 1, 1, the y value 1, you subtract 2 from, and that takes us down to 1, negative 1. And then 4, 2, I subtract 2 from the y value, brings us down to 4, 0. And if I come out here to 9, 4, 5, 6, 7, 8, 9, 9 would go up to 3. So this graph got a little off of where it was supposed to be. And I subtract 2, that brings it down to here. So now my new graph goes like this. It's everything's been shifted down 2 units. Okay. So the function is basically the square root function where you're subtracting 2 from it. All right, so here we're going to have a table. Oh, and they talked about this aspect, that g of x is the same as f of x minus 2, because we're changing the y values of f of x. We're not changing the x we're using, we're changing the y we're getting. Okay. So this table shows that we're subtracting 2 from each of these y values. So these are the new y values that go with the old x values. So everything got shifted downward. So it's the same graph, but instead of going up, you're going down. The domain didn't change, but the range did. The range changed. So now my lowest y value is now -2, and it goes up from there. So that's why it's the interval from -2 to infinity, including -2. Now, vertical shifts, notice they're talking about a positive real number k is added to the output of a function, or it is subtracted from the output of a function. So if you're adding or subtracting a real number from a parent function, then you have a vertical shift. If you're adding it, then it's a shift up. If you're subtracting it, then it's a shift down. That many units, whatever you're adding or subtracting. If I'm subtracting 3, then I'm shifting it down 3. If I'm adding 25, then I'm shifting it up 25. If I'm subtracting pi, then I move it down pi units. All right. Now we're going to talk about horizontal shifts. Now I'm going to change x before I go to the parent function. Whoa. So here's the absolute value of x function. Goes like this. So this is the 0.11, and then we have the 0.22, the 0.00, and the -1, 1, and the -2, Okay. It's a straight line parabola. It's one way of looking at it. So this is f of x, which is just the absolute value of x. Now, g of x is the absolute value of the expression x minus 2, right? X minus 2. Which means I'm changing my x values. So that means I'm changing 0, 0. I'm changing where 0, 0 starts from. So I want to look and see where x minus 2 equals 0, and that tells me where my new 0, 0 is. So x equals 2. When x is 2, I get 0. So when x is 2, boom, I move it over this way. So I'm moving my x values 2 units to the right. So that means 1, 1 gets moved over 2 units to 3, 1. And 2, 2 gets moved over to 4, 2. So the right arm of this graph goes up like that. The left arm, well, I'm going to add 2 to a -1, which brings us to the 0.11. And -2, 2, Adding 2 to the negative 2 gives us 0, so that moves this point over here to 0, 2. And so the left side of the arm, the left arm of the function goes like that. So my function gets moved over to here. The graph gets moved over 2 units to the right. So they're saying this is basically the absolute value function. So I'm changing my x in here. So this is the same as f of x minus 2, which is what they're going to say here. Oh, they're not saying it. Okay. So from my point of view, this graph can be a little confusing. So I'm adding 2 to the x's, but I'm not changing the y's, because that's what happens when you're doing a shift. The x value changes and it drags the y value along with it. But the y value doesn't change, it just is dragged over to the new x value. So negative 2 became 0, and this 2 got dragged over. Negative 1 got changed to positive 1, and this 1 got dragged over to the new y place. This 0 became 2, but this 0 stayed 0. This 1 became 3, but this 1 remained 1. Okay, so that's what's happening. I'm just adding 2 to the x values, and the y values remain the same. The x coordinates on the graph are of G are 2 units larger than the corresponding x coordinates, the graph of f for any given y coordinate. So the x values get moved over 2 units for each y value. All right, so here they're talking about where g of x is just f of x minus 2. We conclude that the graph of g is identical to that of f, except it is shifted horizontally 2 units to the right. Well, that's what we've been saying this entire time we've been talking about this. Okay. The domain didn't change, even though we changed our x values, because the domain was all real numbers. And generally speaking, when the domain is all real numbers and you do some kind of transformation of it, it's not going to change the domain. And the range didn't change because we didn't do anything to change the smallest y value. So now they're asking for a different one. All right, so instead of dealing with x minus 2, now we want to see what happens when it's g of x is x plus 2. So I'm going to do the same thing I did up here, and I'm going to set the argument of the parent function. The parent function is a square root. So what makes that argument equal to 0? Well, in this case, it's negative 2, because I'm going to subtract 2 from both sides. So when x is negative 2, y is 0. So now I'm shifting this point here, because this is from the parent function. I'm shifting it to the left 2 units to here. Because now negative 2 gives me 0 instead of 0 giving me 0. And because I shifted it 2 units to the left, that means all the all the X values are going to be shifted 2 units. So this one is going to be shifted 2 units this way. This one's going to be shifted 2 units this way. This one's going to be shifted 2 units this way. And this one's going to be shifted 2 units this way. So here's my new graph. I wish this thing had the ability to change colors, but it doesn't. Questions on this? So a vertical shift is changing the Y values, and a horizontal shift is changing the X values. Now, a shift up, you're adding, but to get a horizontal shift to the right, you're subtracting. So it's kind of opposite, kind of counterintuitive as to exactly what's going on there. And so is basically absolute value function. And so what they did here, like on the previous one, they just subtracted 2 from each of the X values to get the new X values, and the Y values remain the same. So the X coordinates on the graph of G are 2 units smaller than the corresponding X coordinates of the graph of F for any given Y coordinate. So this statement here, and I think they did it before, is your new 0, 0 is no longer at X equal to 0. Now it's at X equals -2. Yeah. Okay. And so they talk about that now our F of X is now F of X plus 2. So the argument changed, not the Y value. Okay, we conclude that the graph of G is identical to F, except for that it is shifted horizontally 2 units to the left. When you add to the X, it's a shift to the left. If you subtract from X, it's a shift to the right. The domain remained the same, and so did the range. Okay. Horizontal shifts. If the argument X of a function is replaced by X minus H, where H is greater than 0, then the graph of the new function, this phrase here, X greater than 0, means it's a positive number. Then the graph of the new function is horizontally shifted H units to the right. If the argument X of F is replaced by X plus H, again, where H is a positive number, then the graph of the new function is shifted horizontally to the left H number of units. So where plus and minus are kind of plus usually means to the right and minus usually means to the left. But when we're dealing with X and we do X minus or X plus, X minus means we're going to the right, and X plus means we're going to the left. X minus means you're getting positive numbers, and X plus means you're getting negative numbers. Okay. So the graph of the function, oh, this graph. Okay, coolio. So what I want to start with, and I'm going to try and graph all the changes here on one graph. So x squared. So we have the 0.00 and the 0.11 and the 0.2, 1, 2, 3, 4, and the point. Well, I'm going to go ahead and put it on here, even though it won't be on the graph, on the completed graph. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just putting that point on there to get a sense of scale or direction here. So this point and that point and that point. Because x squared is symmetric with respect to the y-axis, these are the images across the y-axis. Oops, it's easier for me to draw it this way. So why didn't I do that in the first place? Okay. Now, I don't think the textbook doesn't do it the same way I do. So we're going to start with this graph. Now, this is y equals x squared. Well, the first thing we do here, I always look to see, am I changing the x? Well, I am changing the x. I'm changing the x to look like x minus 3 squared. So I'm changing my argument x to be x minus 3. So that means I want to look at what happened to my 0, 0. So I set that equal to 0. So x equals 3. So now my 0, 0 went from 0, 0 to 0, 3. I mean 3, 0. Sorry. Because now 3 gives me 0 instead of 0 giving me 0. So that means all of these points here got moved 3 units to the right. All of these points get moved over 3 units to the right. So I'm going to change this. So 1, 1 got moved to, I'm adding 3 to the 1, and so that's going to be 4, 1. And then 2, 4 got moved to 5, 4. And 3, 9 got moved to 6, 9. I just added 3 to 3, and I added 3 to 2, and I added 3 to 1, I added 3 to 0. Now I'm going to add 3 to negative 1, because this is a point negative 1, 1. So I'm going to add 3 to the x value, which gives me 2. So that comes over here to 2, 1. Negative 2, 4. Adding 3 brings me over to 1, 1, 4. And then a negative 3, 9. I'm adding 3 to negative 3, which gives me 0. Gets moved over to 0, 9. So now here's where my graph winds up. So that's this graph. So I'm almost done. Now I have a +2 there. The +2 happens after the parent function. The parent function is squaring. So now the +2 means I'm adding to the y values. So the new y values, which are the same as the old y values, I'm going to add 2 to them. So 9 plus 2 is 11. So this point got moved up to here. 4 plus 2 is 6. So that point got moved up to here. So this is the point. This is 0, 11. And this is the point 1, 6. Okay. And this 3, 1 gets moved up to 3. What is that? 3, 3. 4, 1 now gets moved up to 4, 3. That's this point. 5, 4. I'm gonna shift the 4 up to a 6. So now that's 5, 6. Went from 5, 4 to 5, 6. At an inch growing, 2 inches of growth. And then 6, 9 goes up to 6, 11. Which is about there. And so now I have the new graph. Whoa, I didn't do, uh-oh, I missed it because I forgot to do this point here. So that's going to be 3, 3, 2. So what happened is this graph here, the original graph, got shifted 3 units to the right and 2 units up, because that's what happened to my 0, 0. My 0, 0 got moved 3 units to the right and 2 units up.
Sir, I have a question.
Yeah.
On the graph function, when it says +2 is from, like, it means from it's going up.
Yeah, this +2 here at the end.
Mm-hmm.
Yeah, that means I'm adding 2 to the y value.
Oh, okay.
So I'm changing the y value.
Yeah, I was worried, like, why did he go up? Like, thank you,
Yeah.
sir.
If it was -2, then it would have been going down 2. Because it as we'll discover a little later.
Yeah, it represents
is-
like a negative, and it goes
This
down.
is the vertex form of the equation of a parabola, where 3, 2 is its vertex. Boom. Here we have the vertex right there. So I did the change in the y, change in the x, and then the change in the y. So I did the horizontal shift and then the vertical shift. I could have done the vertical shift first, up 2 units, and then do the horizontal shift. So I'd go up 2 and to the right 3 instead of to the right 3 and up 2. I still wind up in the same place.
So it's in different forms, but the same answer. It should
Well,
be.
it's what are you starting with? I start with my changes in the x, and then I go to my changes in the y. Sometimes the textbook starts with the changes in the y and then the changes in the x. And when we start throwing in compressions and stretches, sometimes they start with the change in the y, and then they go to the change in the x, and then they go back to the additional change in the y. So I just always start with the change in the x. And I do all the changes that are happening to x, and then I look to see what happens to y.
So for the y value, how do I know that it's gonna be y value? Because I think it's because the x minus 3, it says it's the x value, and the plus 2, it doesn't say is the y value. So I think it's the only option, right?
Well, because what we have here, once we do this, we get y.
Okay,
Correct.
I just
This is the y value. This expression here is the y value.
yeah, I understand.
Okay. The parent function is x squared, right? That's the parent function. And I'm going to add 2. The square is the parent function, and I'm adding 2 to the parent function. Well, this is the parent function here, which gives me this second graph I did here, this one here. Okay. And then I add 2 to those y values. This plus 2 outside here is always the change in the y value. If it was a minus 7, then instead of going up 2, I would have gone down 7. And the whole graph would have been moved down here. Okay. And so that they did it the same way I did. So they looked at the shift of the function to the right, 3 units. And then they looked at the change in the y, which is a shift up 2 units. So they basically did the same thing, except they just didn't do it all in one graph. They did it on, they did it on separate graphs. The domain didn't change, but our range did. For x squared, the range starts at 0 and goes to infinity. And it includes 0 because it does equal 0 for the y values. But for the final function, the smallest y value is a positive 2. So the new range is from 2 to infinity, because we changed the range of the parent function from being 0 to infinity to 2 to infinity, because we changed the smallest y value we can get. By adding 2 to it. Now we start talking about stretches and compressions. Vertical stretch, okay, whenever we're talking vertical, we're talking about what happens to the y value. Okay, in this example, g of x, all I'm doing is multiplying f of x by 4. Whoops, I'm not supposed to be an x in there. So I'm changing my y value of the x of the f function. So that's a vertical change. And I'm changing it by a factor of 4. That means I'm multiplying by 4. Okay. So the left 2 columns are for the square root of x. Square root of 0, 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. But I'm going to take each of these y values and multiply it by 4. So now 0, 0, 0 goes to 0, 0, didn't change. But now 1, 4 goes to 1, 1, 1 goes to 1, 4. So this point here got moved up to there by multiplying the y value by 4. 4, 2 got moved to 4, 8. This point here got moved up to here by multiplying the y value by 4. And same thing with the 9, 3. 9, 3 went to 9, 12. So this point here got moved up to there. And then we just have the graph of the line that fits those points, the curve that fits those points. So we're multiplying each of the y values on this curve by 4 to get up to here. So I am stretching the graph up. Well, in this case, it's up. I'm stretching it away from the x-axis. So a vertical stretch is pulling it away from the x-axis because I'm multiplying the y values by a number. So I'm either making them more positive or more negative. It just depends upon what the y value is. If it was a -3 and I multiply by 4, that gives me -12. So it goes further away from the x-axis. So if the y value was here, now the new y value is up here. If the y value was here, now the new y value is down here. So I'm pulling it away from the x-axis. But since for a square root function, we're only dealing with the positive x values, so we only get positive y values. So it's pulling it up away from the x-axis by multiplying by 4. And 0 stays anchored at 0 because 0 times anything is 0. Okay. Any questions here? You know, a vertical stretch is pretty straightforward, just like a vertical shift is pretty straightforward. With a shift, you're either subtracting something or adding something to the y value. Here with a stretch, you're either multiplying something times the y value. All right, there they were multiplying by 4. And this is the same problem. This is the same graph. For each x value, the y coordinate of a point of the graph is 4 times as large as the corresponding y coordinate of the graph of f. And so they're just saying the same thing. We're multiplying each y value by 4 to get the new graph. Okay. Yeah, so here they're talking about what I said to begin with. And that's what I always look at. I look at what's happening to f. What's happening to the parent function, okay, or the key function. This textbook calls them key functions. Okay. So the graph of f of x equals the square root of x is vertically stretched by a factor of 4 to obtain the new graph. The graph of g. All right, so yeah. Now we have x squared. X squared. We all love x squared, don't we? X squared is a good one to use. It's a good because we can see a lot of what's going on there with x squared. So actually, I'm going to go out 3. 1, 2. Oh, and 3 won't fit on here. So 1, 1 is here. 1, 2 goes to 4. So that's 1, 2, 3, and 4. So here we have this side, which goes up. Thomas, you silly git. Okay. And then on the other side, it's just, they just 1, 2, 3, 1, 2, 3. Is that right? Yes. Okay. I should have just done 2 because it's 1/2. So this is y equals x squared. And so, or f of x, let me do the f of x equals x squared. And what g of x does is do 1/2 of x squared. So g of x is
Hey, sir,
1/2. What?
I think your screen just froze because I can see anything from where you're writing for.
Okay, this happened in my
Yeah, the other
other
classes.
class. Yeah, this exact same thing happened. Okay, so what I'm going to do is, you know what? I'm not going to bother with that. I'm just going straight to this. And I will, come on, go to my task manager and find Zoom. And in the task,
You're on mute, sir.
I don't care. Okay, yes, I do. Wow, that did it real quick, didn't it? There's that. And not that, I want that. Now I pull this back up so I can do the share. Well, it'll be nice when they get me the room key so I can do this on the computer in the classroom that they're allowing me to use. Because the school, what do you want to call it? Wi-Fi network doesn't like me very much, especially when I start using, well, when I'm using Zoom, it'll freeze it up on me after a while. Whoops. Here we go. Thank you for notifying me that that was happening. There we go. So what was I saying? Oh, that g of x is 1/2 of f of x, right? Since f of x is x squared, then this is just 1/2 of f of x. So whatever the y value is, because x squared is the y value of f, I just multiply that y value. This is the 0.11, and this is a point -1, 1. This is the point -2, 4, and this is the point 2, 4, and here we have the point 0, 0. I'm going to multiply those y values by -2. I mean by 1/2. I multiply the y value. So 1/2 of 4 is 2. So this point -2, 2 comes down to, let me see. To 2, 4. Well, wait a second. Is that at 4? 1, 2, 3. Oh, this is, I missed those points by 1. Okay. So, So now it's at -2, 2. And I'm going to take 1/2 of 1. And so that's going to bring us down to here to 1/2. So -1 goes to 1/2 now. 1/2 of 0 is still 0. And then 1/2 of 1 is 1. So that's this point here, 1, 1/2. And this point is 1/2. So it's here now.
Yeah,
And that's at
so
2, 2.
the screen just moved.
Oh, this,
We can only see
whoa.
the PowerPoint.
Where is it? There it is.
Thank you, sir.
Okay, I don't know how that happened. I must have hit something to make it happen. And so my new graph, whoops, I want the thick line, goes like this. So if I had 3 on here, it would come down to 4.5. So 339 would come down to 4.5, and -39 would come down to -3, 4.5. So all of these points, let me go back to this, because this line got changed a little bit. Okay. Just gonna erase that point. Maybe I'm gonna erase that point. Okay. So all of these y values got taken in half. So a vertical compression, like a vertical stretch, is multiplying the y values by a number. And now we're compressing it towards the x-axis. Where a stretch, we were pulling it away from the x-axis. So if instead of multiplying by 1/2, what if I was multiplying by 2? So this point would have been pulled up to here, and this point would have been pulled up to 8, which is off of my screen. This one would have gotten pulled up to here. And so, but that would have stayed there. So it would have been a much narrower graph. Because my y values are being pulled up or being pulled away from the x-axis. Okay, so each y coordinate of the point of the graph is 1/2 as large as the corresponding y coordinate of the graph of f. So that's what I did here. So the graph of f is vertically compressed by a factor of 1/2 to obtain the graph of G. So their picture is prettier, but I think it's easier to see the compression here with the expanded scale. The expanded scale is what I meant to say. Okay. Questions? Now, vertical compression and stretches. Here's a summary of what we're dealing with. A function f of x is multiplied by a positive number a. Okay. The graph of the new function a f of x is obtained by multiplying each y coordinate by a. So that's just a straight multiply. If a is a fraction, a positive fraction less than 1, then you have a vertical compression. If a is a number greater than 1, then you have a vertical stretch. So if it's in this case, a equals 1/2, which is a positive number less than 1. So we had a compression. We compressed it towards the x-axis. And the previous problem, which had 4 times the square root of x, there a is 4, which is greater than 1. So that we had a stretch. Now we're going to be talking about horizontal compression or stretches. Where a vertical, we're compressing it towards the x-axis. A horizontal compression or stretch, we're moving it towards or away from the y-axis. So we're compressing it left and right as opposed to compressing, stretching up and down. They use this particular function a fair amount of times in pre-cal. I mean in college algebra, because when you get to pre-cal, you're going to be looking at this and doing things with this a lot. So this is a sine function. It's -2 sine. I mean 2 sine of x. But anyway, so here we have -pi/2 and then -pi and 0 and +pi/2 and pi and 3pi/2 and then this is 2 pi. So what happens here at pi, it's at 0, even though they just have an arrow there on the picture. It goes through 0, 0. I mean through -pi/0, and then at pi/2, it's at 2. Well, I'm going to have this be 1, 2, so this is up to here. And at 0, it's 0. At pi/2, it's at -2. So 1, 2, -2 down here. And at pi, it's back to 0. And at 3pi/2, it's back up to +2. And then at 2 pi, it'll be back to 0. And so the graph goes something like this. This is an odd function. It's symmetric with respect to the origin. Okay, so on this one, we're multiplying the f function, this function here in blue, this one here. We're multiplying the y values by 3. Oh, damn it. So that's 3 and 4. And so it's going to go higher than what I have here. Oh, crap. So I'm going to have to redraw this so I can have those on the graph. Put this in the middle. So I have 2, 1, 2, 3, 4, 5, and 6, and 1, 2, 3, 4, 5, and 6. And this is a negative pi over 2 and negative pi, and then we have pi over 2 and pi and 3 pi over 2 and 2 pi. And so here it's 0, here it's at 2, here it's at 0, here's at negative 2, here's at 0, here's at 2, and it comes back to 0. So just drawing the same thing, quick and easy. It's just a little time consuming. Okay. And so there's that function. And so this is f of x. And so when I multiply 3 times f of x, that means we're multiplying the y values by 3. We're going to keep the same x values, but now this is the point. What point was it? Negative square root, negative pi over 2, 2. So I'm going to multiply the 2 by 3. So that's going to go up to 6. So that's 4. Oops. No, that's 3. 1, 2, 3, 4, 5, and 6 up here. So that's 6, and that's 2, 4, 6, negative 6. Okay. And then 0 times 0 is still 0. And then this point down here, I'm going to multiply the y value by 3. So negative 2 times 3 is negative 6. So that point comes down here. And then I'm going to multiply this y value, which is 2 again, by 3, which brings us back up to 6 here. And then at 0, it stays 0. And so this is my new graph. Let me change it. So it's going to come up like this. Go through, make a sharp turn. Come back through here. And go all the way down to this one down here. Make a sharp turn again. And come back up. And go through that point. And go through there and come back down again. So each of these y values here got multiplied by 3 to get the new y value, and the x value remained the same. So that's what happened with. So this is y equals 3 times f of x. All right. It's a vertical stretch. So we're multiplying the y values by a. The next one is y equals f of 2x. So I'm changing the x value before I do the function. So that's going to be a a horizontal. In this case, it's going to be a compression because the reciprocal a is 2. So I want the reciprocal of a, which is 1/2. So now I'm going to multiply each x value by 1/2. So that's going to be squeezing this one in towards the y-axis. So this one's going to be moved that way. This point's going to be moved that way. This point's going to be moved that way. This point and this point, they're all going to be moving towards the y-axis now. For this one, for A, they were being pulled away from the y-axis. But now we're moving it towards away from the x-axis, but now we're being moved towards the y-axis by multiplying by 1/2. We multiply each x value by 1/2. So negative pi times 1/2 becomes a negative pi over 2. So this point got moved over to here. And negative pi over 2 got multiplied by 1/2, which is a negative pi over 4. So this is negative pi over 4. So that means this point got moved to here. Half of 0 is still 0, so we stayed at 0, 0. 1/2 pi over 2 times 1/2 is pi over 4. So this is pi over 4 here, this here. So this point got moved to here. Pi multiplying pi by 1/2. Pi times 1/2 is pi over 2. So this point got moved back to here. Three halves pi. Running out of room down there. So 3/2 pi times 1/2 gives us 3 pi over 4. Well, 3 pi over 4, 3/2 pi is back to here, 3/2 pi. So this point, I'm sorry, this point here gets moved back to here. And it ends up, this point here, which is at 2 pi, gets multiplied by 1/2, which is just pi. 2 pi over 2 is pi. So this point gets moved over to this point. So now my graph comes up like this. Oh, let me change the. So it comes up like this. So the original graph, f of x, got squashed, got put in a squeeze plate and got scrunched in towards the y-axis. And so the 3 is outside the function f. So we're changing the y values. If the change happens outside the f function or the parent function, then you're changing your y values. In this case, we're multiplying by 3, and you could be adding 1 or something like that. Okay, and so then yeah, and then that's what they did there. They got that's what their graph is what I have here for this one. All right. Now, the 2 is inside the function. So we're changing the x before we apply the parent function. So that means I'm multiplying by the reciprocal of a. A is 2, the reciprocal is 1/2. So we're multiplying each x coordinate by 1/2. So now all the points get shifted towards the y-axis. Okay. Any questions here?
I'm gonna take a screenshot, sir, for the.
Okie doke.
Thank you, sir.
Okay. Now we're going to talk about a reflection. A reflection about the x-axis means I'm just flipping it upside down. What was up is now down. What was down is now up. X squared goes something like that. So when I do the negative of x squared, I'm changing my y values. Okay, the minus sign is outside of the f, or outside of the parent function. So I'm changing my y values. So I'm flipping it across the x-axis, because what was positive is now negative, and what was negative is now positive. And since the since the range of the square root function is non-negative numbers, then the range of the new function is going to be all non-positive numbers. So from 0 to the negative. So it's going to come up from the negatives and stop at 0. So my range now goes from negative infinity up to 0. That's the range. That's the numbers I get out of the function. The numbers I put into the function are still going to be the same numbers. It's all real numbers. So f is basically the square root function. So we start with, I think they meant to say y equals the square root of x. And so that would be this thing. And then you just change the sign on the y values. So for each point x, y on the graph of f of x equals the square root of x, the point x negative y is on the graph of f of x equals the negative square root of x. So I'm just changing my y values of the parent function. So the point 0, 0 stayed 0, 0, but 1, 1 became 1, negative 1. 2, 1.4 became 2, negative 1.4. 3, 1.7 became 3, negative 1.7. 4, 2 became 4, negative 2. Okay. Simple, just changing the sign of the y values. When you change the sign on the outside, you're changing the sign of the y values. The domain didn't change, but the range did. Okay. So a reflection about the x-axis, when a function f is multiplied by -1, the new function y equals negative of f of x is a reflection about the x-axis of the graph of f of x. So which was, yes?
Oh, I'm sorry, quick question. So if it's more than -1, would it be a reflection and a stretch, or is it no longer considered a reflection?
Well, when we talk about reflections, we're talking about just the negative sign.
Okay.
So it'd be -1. So if there like if we have -4 times f of x, then we look at them separately.
Yeah, okay.
We'd
That's
look
what I
at
just
the
wanted to make sure on.
-1 as a reflection, and then we would look at the ×4 as a stretch.
So
we
you do
would-
them separately at that rate.
Yeah, we would do them separate. And that's what the textbook does. It does them separately. I tend to put them together because, yeah, -4, you're multiplying by -4. So you're doing the stretch and the reflection at the same time.
Understood.
Okay. And which is something I don't normally do. I usually do it one thing at a time. I don't do 2 things or 3 things at once, especially when I'm trying to explain it. So now here we have the negative sign is before the parent function. The parent function is x cubed. So I'm changing my x value. I'm changing the sign on my x. So that's a reflection across the x-axis, not the y-axis. So now, helps if I could draw it right on the line. You know that? So now I'm flipping this way. So if it was on the left, now it's on the right of the y-axis, and if it was on the right of the y-axis, now it's on the left. So this point gets moved over to here, and this point would be moved over to here. So the mirror image happens left to right, where with the other one, the mirror image happened up and down. So here I'm changing the sign of my x's. So with cube root with cube, okay. -2 gives me a -8. -1 gives me -1. 0 gives me 0. 1 gives me 1. And 2 gives me 8. So I'm just looking at the ordered pairs. And what this is telling me is I'm going to change the sign of my x value, but I'm keeping the y value. So this point goes to 2, -8. This point goes to 1, -1. This point stays at 0, 0 because -1 times 0 is still 0. And this point goes to -1, 1. I'm multiplying the x values by -1. And 2, 8 goes to -2, 8. So this point here went over here to this point, and this point down here went over to this point. And then at +2 would be up here at 8 somewhere, and so 1, 2, 3, 4, 5, 6, 7, 8. This point got moved over to here. The x value changed its sign. -1 went to +1. So -1, -1 went to 1, -1, and then -2, -8. 5, 6, 7, 8. -2, -8 comes over here to +2, -8. So it got moved over to there. So now the function comes, and 0, 0 stayed at 0, 0. So now the function comes through like this. where originally it had been over here like this. Whoops, gotta make that turn right. So what was dashed is the original function, and now the new function is a solid line. And their graph looks better because I use blue and black. Okay, so the graph, we begin with the graph of f of x cubed, and then for each point xy on that graph, we change the sign of the x value, and the y value remain the same. And so that will show us the reflection. And that's what they did here. Yeah, I don't like the way this particular thing looks. Oh, okay. I see what they're doing. So this point went over to here. This point went over to here. This point stayed there. This point went over to there. This point went over to there. Okay, so it matches what I did. Now here's with an odd function. This is an odd function. So with an odd function, a reflection about the y-axis looks exactly like a reflection about the x-axis. This reflection about the x-axis looks exactly like a reflection about the y-axis. So if this was the negative of x cubed is going to look exactly like the negative. Those two are the same thing. So this is a reflection about the about the x-axis, and this one's a reflection about the y-axis, and the graphs are going to look exactly the same. Although how you get the numbers is different. Okay, so the domain and range don't change. It's still all real numbers for both the domain and range. So a reflection about the x-axis when a graph of a function f is known, the graph of the new function y equals f of negative x is a reflection about the y-axis of the graph of the function. So that's just saying that. Yeah, so we're flipping it across the y-axis. Determine the function obtained from a series of transformations. So we're starting with x squared. Y equals x squared. So I'm shifting it 3 units to the right. So that means I'm changing my x values because it's a shift to the right. Okay. So a shift to the right means we're subtracting from the x in the function. So this is going to be x minus 3 squared. This shows the shift to the right 3 units. So that means x squared here got moved this way 3 units. And there we have it. Okay. So a reflection across the x-axis. So that means I'm going to do what's inside here. What's inside here, I'm going to reflect what's inside here. Which what happens is when I take that negative sign inside, I get a negative x plus 3 being squared, or I could write that as 3 minus x squared. Either way would be correct. but I would tend to write it this way. Reflect about the X. Oh, I misunderstood. I totally misunderstood. A reflection about the x-axis is mean we're changing the y values. We're changing the sign on the y values. So that's going to be the negative of these y values. In my head, I was thinking across the y-axis. I don't know why. Because it was x. Okay. And then shifting down 2 units, again, we're changing in the y units now because a shift up or down is a change in the y units. So that happens after the function. So we're shifting down 2. So that means we're subtracting 2. So we're going to take these y values we get here and we're going to subtract 2 from it. Boom. So if I multiplied this all out and simplified it, that would give me the quadratic. And it opens downward because this is negative out here. Okay. The domain and range of f. The domain, I'm just going to start throwing numbers in for x. Can I put in, are there any restrictions on numbers I can put in for x squared divided by 2 plus 1? Eh? All right, what they did here, they wrote it as 1/2 times x squared plus 1. So the 1/2 and the plus 1 are changes after f of x. Okay. Because so that's changes in the y values. I'm not changing my x values. I'm only changing my y values. So since for x squared, the domain is all real numbers, that means the domain here doesn't change. So it's going to be all real numbers. Now, what happens is we take half of each of the y values and then add 1 to it. So for x squared, 0, 0 is the smallest y value, and we go up from there. So taking half of each of those y values makes the graph compress towards the x-axis, and then the plus 1 is adding 1 to each y value. So now my smallest y value is 1, and my largest y value is infinity, and so there's my new range. So the square function, and then multiply each of those by 1/2, each of the y values by 1/2, and then we add 1 to each of those new y values, and we look at the smallest y value to the largest x value, the smallest y value to the largest y value. And so that's from 1 to infinity, or in set builder notation, it'd be y, all real numbers y such that y is greater than or equal to 1. Okay. First of all, this one I would rewrite as x plus 2 square rooted and then add 1, and we have a negative sign out here. Now we're having a horizontal shift, we're having a vertical shift, and we have a reflection. And we do the reflection about the x-axis before we do the vertical shift. Okay. But we're at time, so let's just say you're not going to have this type of problem on the test. As far as transformations are concerned, I'm concerned about the steps involved. This shows more complicated steps than I want you to demonstrate. You will have to do this for the homeworks. The homework, this is the degree of difficulty. The homeworks are more difficult than the review, and the review is more difficult than the exam. So if you can do the homework without too much trouble, you should be able to do the review without much trouble, which means you should, the exam should be a cakewalk. Which means it should be easy for you. And so I'm going to stop the share because I'm selfish. And I'm going to move my Zoom back over to this window. Unless you have questions for me, you're free to go.
I had a question, sir.
What? Have several people clamoring for attention. Okay. What is it?
I had a question, sir, about the, I always see the my lab that you're taking this class, like how can I say it, like the screen problems, and I don't see on my lab. I don't know if I can find it on my lab. It always says errors and just show the assignments. Also, I just look for the chapters and stuff in person, and I can look up those. I don't know if it's an error or something, or it's just like that.
I'm not sure I'm understanding what your question is.
Like I want to see the chapters of the things that we are looking at it.
I think he's
From the
talking about the.
classes.
I think he's
Okay.
talking about this. I think he's talking about the stuff you show on the screen.
Oh, okay. I think I understand. Are you trying to figure out like what chapters, like the the stuff we're going over is on my lab?
Yeah.
Okay. Basically, he's asking which assignments on my lab are for this homework, for this
Oh,
this meeting.
what section are we in for as far as the, let me pull that PowerPoint back up. We're in, all right, so we did section 2.5 today. So everything up to 2.5 will be on the exam. Everything
just-
up to 2.5 is the homeworks that I expect to be done for the exam.
Understood.
Okay. So was that what your question was about?
Yeah, I'm just was going to review the past assignments.
The doing the homeworks is a good review. So
I think he's also saying like, how can we like look at what we learned, like the notes that you took.
well, I'm going to put out a review. And if it's not on the review, it won't be on the test. And the review covers in more detail than what's going to be on the test. So there might be some minor points or that are on the review that won't be on the test. Or there will be. Like what we just covered, not all of that's going to be on the test. Some basic understanding of what's happening with transformations will be on the test. That's what I want to get across, is that on the test, I want the basic understandings, how, and in some cases I do want a more complex understanding, but the review, if you can do the review, you should be able to do the exam without any problem. Either my Zoom is slow.
No, I think you're good.
Okay.
I mean, I myself had 2 questions. This is more like, I guess, personal related stuff. Is the class, I mean, is the exam on Wednesday, or is it like on your own time kind of thing? Like
No, it's
outside of
on
the
Wednesday during class time.
Wednesday during class. Okay, I have a wedding to go to on Wednesday, so I'm gonna make them know, let them know I'm late. And then 2, were we gonna need a calculator? I don't think so, but I just want to make sure.
Having a calculator is helpful. For exams, you're allowed to use an exam a calculator.
Okay, so I'll just have one on the side.
So
just in
if
case.
you just have a 4-function calculator, that's fine.
Okay.
I'd rather you not use the calculator in the computer or the calculator on your phone. Just a basic scientific calculator is all you really need for this class.
Gotcha. Okay.
And
So I
you
don't think I
can go-
need one, but oh, sorry, cut you off.
You can go to Walmart and buy a TI scientific calculator for $10 or $11. I don't know how much it is now.
Gotcha. Yeah, they're pretty cheap. Okay, yeah, but just like the main thing I just wanted to go over is like I do have a wedding that day, so I just didn't know what time the exam was, and then I just gotta work around it.
Well, what time is your wedding?
Well, it's not my wedding, it's my brother's. He hasn't specified on times yet, so I'm trying to make sure I have everything going.
Well, let me know. And I have a 10 o'clock class that's also totally online. And I can set yours up to take it at the 10 o'clock hour.
Okay, yeah, I'll get the time for the wedding and then I'll get you updated on that.
So if you want to take it 2 hours earlier, you're quite welcome to do that. I just need to know ahead of time so I can set up, because the way Canvas works, because everything is done through Canvas,
Hmm.
the exam you take through Canvas, and so it will be and I can set up, I can have everybody take the exam at different times,
Oh, okay.
which is nuts on my part, but because that's what
possible.
I've done in the past. People who have who have excuses for missing the exam,
Mhm.
instead of creating a new
Like a new
time
assignment as the
frame,
exam.
I just time shifted the exam for that person.
Okay.
Yeah.
But yeah, I'll go ahead and get the time on that. I'll keep you updated. Yeah, they just kind of like
If
told
you
me out
want
of
to come
nowhere.
in at the 10 o'clock, well, if you can come in at the 10 o'clock.
I don't think it'll be an issue.
Okay.
Okay. Well, thank you for letting me know. I just like I said, they just kind of dropped it on me last second. And I was like, oh, Wednesday. I see.
Okay.
Okay.
So are you
Well, thank-
part of the wedding party?
I am. Yes, but I haven't like got any roles or anything in it yet. I'm gonna be there.
Okay. Are you going to be one of the groomsmen or just an usher?
From what I know, just an usher. But like I said, I haven't got details yet.
Yeah, because I was just an usher at my brother's weddings. Yeah, I don't have a lot to do with my brothers, so they
Yeah, it's
felt
like
obligated to have me part of it. So they made me ushers.
Like it's kind of weird because my brother he moved back up to Alaska like a few years ago, so he's coming down here for the wedding, and I didn't know that until very recently. And then we're now having it on Wednesday, so
Oh, okay.
yeah, it's a weird situation, but I'm not gonna complain. Great
Yeah.
times.
Okay.
Thank you for talking through it with me, and have a good rest of your day.
You too.
Okay, sir. So I have a few questions.
Yes.
One is the thing is I'm a slow writer when it comes to taking my notes, and while you were presenting, and I want to know would you post the video on your YouTube because so I can review it?
Yeah, that's one of the things I'm doing this because I've gotten way behind on my YouTube channels,
Yeah.
and the
Yeah, I was gonna ask you about that.
YouTube had been messing up for a number of people, and I don't know why. So I'm gonna recreate my YouTube channels, and I'll post that.
Okay. Yeah, because that will really help me for the review.
Okay.
Yeah, because I'm not a fast writer.
Okay.
I got other. I think I got a few other questions. Oh yeah, when is the test? Is next Wednesday, right? I mean, the Wednesday's coming up.
And
Okay.
it's during class time, and
Mhm.
it's through Canvas.
Yes. Okay. All right. I
So
think that's it.
in the Canvas menu, there'll be quizzes. It's
Ah.
not there yet because I haven't posted any quizzes yet.
Okay.
Okay.
Yeah. And the homework is only up to 2.5, right? Section 2.5. All right. Yeah, I just want to make sure that everything's all cleared up.
Okay.
All right. So yeah. Just let me know whenever the videos will be posted or something with an announcement, just so I know, because that would be really useful for me.
Yeah, when I put the review in the files, I will send out an email,
Okay.
and I will also make I'll put an announcement and an email, a Canvas email.
All right.
And if
All right.
I think about it, I'll put out an email through MyLab. It's
Okay.
whatever email you used for MyLab will also get an email from me,
All right. Cool.
if I remember to do that. So I don't always remember to do that.
Okay. All right, sir. So thanks for the help.
Okay.
I know I came in late. My Wi-Fi went down this morning, but I just wanted to make sure I was counted for attendance.
As long as you put your name in chat, you're counted.
Okay, do you want me to do it right now? Because I forgot.
Had you hadn't done it before?
No, not today. I haven't.
Okay. Whenever you come into class, that's the first thing you should do is put your name in chat.
Okay.
And whether Zoom kicks you out or not, you're there. Because I have a lot of people who have issues staying in.
Okay, I just put it right there.
Okay.
Thank you.
Sure. We'll see you later. And what's going on now?